So I will talk about mostly competing with switching lattices today. So here is the outline. First, I'm trying to explain what we are doing in our lab in Istanbul Technical University. So mostly about emerging computing, but different topics: reversible, probabilistic, bit digit serial, approximate. And today's main topic is competing with nanoarrays. And under this headline, so I will mostly talk about switching lattices. Switching lattices, why I selected this? Because this journey, switching lattices journey, started during my PhD. So more than 10 years I have been working on this. So I started with the logic and then circuit design and technology and CMOS design, layout, fabrication, cadence. So lots of stuff here. That's why I will talk about switching lattices. So what is emerging computing? When someone tells you emerging computing, so kind of tricky. On the one hand, in academia, something emerging means something maybe novel, so which is good. But you should be careful because most of the emerging stuff in the literature, so you couldn't find a good, feasible, concrete application. So if you're doing something emerging, application has a crucial role. So that's why in our lab, we are always trying to find a good application. For example, reversible computing. We wouldn't tell that, okay, reversible computing is the future computing paradigm, can be used in quantum computing. Future computers will be all emerging, all quantum, not like this. So these are good, of course, this is research, but we're trying to find a concrete technology and application all the time. So that is the role in our lab. So let's, for example, talk about emerging computing. So briefly, I will discuss this computing paradigms. So as you guys know, emerging computing, reversible computing, there is one-to-one matching between input and output, meaning that whenever you see the output, you can predict the input. Normally, and this is two-way computing. Normal, conventional computing is not like this, right? So for example, on the right-hand side, there is a basic AND gate. Even for an AND gate, very basic, right? 2 input and 1 output, you cannot tell the input just checking the output. You can just tell the output when checking the input. So in conventional computing, that is the whole purpose. So inputs are determining the output, but vice versa is not applicable. Okay, what you might say, what is the problem here? The problem is that whenever there is a fault in reversible computing, reversible circuit, you will immediately see it at the output. But in conventional, it's not. And in logic, we call it don't cares. And the don't cares might be dangerous, right? Because there's a problem, but you can see it. You will see it for sure in the future. And for this purpose, we use reversible computing. Reversible computing to detect faults 100%. And here, this is important. So we have not realized reversible circuits, because reversible circuits are two-way circuits. Reversible computing is good for quantum, but not good for CMOS. But we have exploited reversible computing to generate 100% fault detectable CMOS circuits. So at the middle part, it is like a dummy. We use reversible, but at the end you have a CMOS. And we have done all the simulations and technology and stuff. This is good. And we have US patents from this research. Again, if you have any questions, feel free to ask. The second one is probabilistic, stochastic computing. Stochastic computing, as you guys know, inputs are probabilistic. So there's probability of having one for each bit.
I have a question.
Yes, go ahead.
What is the advantage of reversible computing in the modern computation? Can you explain about it?
You mean in our research, or is it a general question?
It's a general question.
So reversible computing, so as I say, it is two-way computing, and there is one-to-one matching, meaning that for any reversible circuit, so our circuit is not a real reversible circuit. For example, quantum circuits are reversible. Whenever you see the output, you know all the values in all nodes in reversible circuits. So, for example, cryptology, which is great. So you can follow the problem. So one by one in reversible, starting from the output. For example, output, you have a warning. Your information is copied, right? So you can follow it all the way to the beginning in reversible computing, because reversible computing, so input and output can change the roles, not like conventional computing. Does that answer your question?
Okay, thank you.
So second one, probabilistic computing. Again, briefly. So probabilistic computing, instead of working with deterministic values, for example, you can represent 3 with 2 bits in deterministic, but here we work with probabilities. Okay, what is the advantage of doing so? The advantage is the area. The advantage is the area. Why? Because in conventional computing, for example, there's a good example here. Multiplication, multiplier, this is 3-bit by 3-bit multiplier. So you need maybe 100 transistors and maybe tens of gates. But in stochastic computing, multiplication just needs one AND gate. And it is independent of the input resolution, meaning that, for example, 16-bit by 16-bit multiplier needs like maybe thousands of gates. But in stochastic, it's always one AND gate. But what is the problem here? So kind of not logical, right? Just one gate doing everything, because multiplication and for addition also similar. If you do multiplication, if you do addition, you can do anything, right? But the problem is that the bit streams are too long. So delay or latency, so big headache. And in the big picture, stochastic computing is not good if you compare energy values. Okay, then what? How about the application? What's the application that stochastic computing can really work? There should be an application such that it can be feasible only with like few transistors or gates, meaning that for a certain technology you cannot, it's impossible, not feasible to use hundreds of transistors. What is this application? This application is large area, flexible electronics, for example, organic transistors. So organic transistors, I mean, it's not quite feasible or commercially used that. So there is a flexible circuit with thousands of transistors. So for this purpose, stochastic computing can be used.
Well,
but
sir,
from my, yes, go ahead.
if you connect X and Y together, it will not work, right?
No. They should be independent.
So you're making that assumption, right?
Yes, and it's a good question. So they should be independent, and you should satisfy this, meaning that you should generate this X and Y independently, or there are other techniques to generate a couple of signals from one signal semi-independently. So, but independent, yes. So currently we haven't, I mean, we are not doing research on probabilistic stochastic computing, because in the logic, circuit, and system perspective, I don't see a good picture here. So it is just my intuition. Okay, but the follow-up research that we did, bit and digit serial computing. So in stochastic computing, unary, but unary and probabilistic. So distribution is random. But here, bit digit serial computing, I mean, it has lots of applications. It's commercially used in neural networks, DNNs, and lots of papers there. And we have also published a couple of papers, good papers on this, IEEE papers. So digit serial, bit serial, I mean, has some potential, I think, and good potential. Okay, and the last one is approximate. Actually, approximate computing is, as we all know, it is always good. It's always popular because the motivation is very strong. So for some certain applications, you might not need perfect accuracy. For example, in calculation, right? Calculator. So perfect accuracy is a must. I mean, you multiply 3 by 5, and then your calculator gives you sometimes 15, sometimes 14, sometimes 16. So terrible. Who wants this, right? But for applications, especially for image processing, so, and neural networks, if there is accuracy criteria, so you can do stuff approximately. What is the advantage? Approximate circuits can consume much smaller area and relatively power and relatively energy. So approximate computing, and we have done lots of research on this. This is one simple example. Especially for neural networks, it's popular hardware part of neural networks, because neural networks are lots of adders, right? So if you do a good approximate adder, you can save lots of energy. Okay, this is the main topic today. So after 15 minutes, competing with regular arrays. So the main motivation is doing the competing with regular arrays. Why? The main problem, you have heard this story before, Moore's law. What is this law? So CMOS, so 1963, in almost 50 years, very powerful. And this powerful thing is that, so technology scaling is very powerful. Meaning that, for example, it says that transistor count doubles every year. So you might remember or not, I'm old enough to remember when I was in college. So we bought a computer, for example, in the freshman year, and then after a couple of years, so it was becoming just trash. So no game, nothing, so it didn't work. Why? Because technology was growing and scaling very fast. For example, 1 year, the computers consist of 100 or 100 nanometer transistor, and after 2 years, 50 nanometer. After 4 years, 25 nanometer. What is the point here? So if you're getting to 100 to 50, meaning that roughly you have like 4x area improvement. Relatively, you have 4x power improvement. And there is delay similarly because capacitors are smaller. So in like 2 years, you get everything 4 times better. Then your old computer, it's not old indeed, but so fast. So in these years, in these 50 years, nobody actually checked for a good new emerging computing paradigm. Actually, there was research, but so there is also risk. There's a new computing paradigm, but there's already very good improvement. Who needs a new computing paradigm with some risks with it? Because this conventional computing has its own tools and everything stable. So, but we are getting to the end. I mean, we are at the end, not getting now. So it's slowing down, slowing down. Now it's very slow. So now you can confidently use your computers, but like 2 or 3 years ago, right? Similarly for phones and everything. It is not like the years like a decade ago. So here are some graphs. The summary of what I have tried to explain. Frequency, stuck. VDD, starting from 5 to 1, stuck. In power, almost stuck. L. This efficient L, maybe you have heard the news. Apple has a new technology of 5 nanometer. 5 nanometer technology is roughly, it tells you the L, channel length. The conduction in the channel length. So the smaller the channel, right? So the higher probability that you have current. So smaller length, smaller bit is good. Smaller, smaller, smaller. But it is also stuck. I will explain why. Although you have heard the news from, we are getting from 10 nanometer to 5 nanometer, area is not getting to 4x to x as it was before. So here is another example. So see that from 25 nanometer to 5 nanometer. So your area advantage is very tiny, but fabrication cost is high. If you have a perfect competing machine, of course, you can select 5 nanometer. And if you have customers, rich customers like Apple does, for example, so you pay this cost, but not for everyone for now. So here also we're getting stuck. Another motivation, as I explained, started to explain. So I told you that, for example, from 2x to x, 2L to L, you have 2x improvement in 1 dimension, 4x area improvement in 2 dimensions. But it is not like this, because the layout rules or fabrication rules are quite strict when you are getting under 40 nanometer. For example, you might have heard, so FinFET. FinFET layouts, FinFET chips, I mean, your flexibility in design, in putting these layers, source, drain, and gate, and polys, and metals, and everything, so restricted. Mostly one-dimensional, so parallel to each other. There's an example here. So you cannot do the same thing that you did for planar CMOS, larger than 40 nanometer. For example, these reds are polys. You can draw polys in fabrication, this layout, like this, for 90-degree angles. But in FinFET, you cannot. And spacings are more, meaning that you're getting to 10 nanometer to 5 nanometer, but area advantage, what you expect is 4x, but what you get is 1.2x. That is a challenge also. Okay, from this motivation all the way back to my PhD, how about doing something with regular arrays? Because things are getting regular. And there are 2 ways, 2-terminal and 4-terminal. 2-terminal switch is the regular switch, or CMOS. There are 2 terminals for current conduction, and there's a control. 4-terminal, there are 4 terminals for conduction, and also there's control. Why we offered this 4-terminal switch? Because it is good for the regular array. Because in a regular array, each cross point or each cell has 4 neighbors. So, and you can isolate 2 of these 4 neighbors, but it's also costly. Okay, 2-terminal, this is like not in the last 5 years, but before, there was a good amount of research on this diode-based nanoarrays, like this. So, especially beginning one, and recent years memristors, it can be said diode, so memory diode. FET, field effect transistors, 2-terminal. Okay, so and then we asked this question. Shannon told us in 1938, you can implement anything with two terminal switches. And indeed we did, using thousands of transistors. So this master's thesis is really good. So I suggest you to read. So Shannon from Caltech, so 1938, one of the greatest master's theses of all time. So, and very basic, very easy to understand. So there's, he was genius, and he basically told that you can do anything with two terminal switches. And then CMOS as the technological implementation of two terminal switches came up, and others. And Shannon's work is good. So now, actually doing my PhD, I asked this, okay, we can do the same thing with four terminal switches. But we should first prove that you can do anything with four terminal switches in terms of computing. And to prove this, you should start with the logic. First, you should be able to implement any logic function. For example, in two terminal switches, it's easy, right? So, I mean, if you do not consider area, just the implementation, you can connect these switches parallel and series and get the function. But how about the four terminal switches? How to prove it? And four terminal switch-based arrays consume much smaller area. So here's an example. This is 6 switches and 14. Okay, here is a four terminal switch, open and closed. Closed are black, opens are white. Switches, like all switches, are controlled by Boolean literals, X's and X naughts. So here the Boolean function from top to bottom. So if there's a top to bottom connection from top to bottom connection or closed path, then this FL becomes 1. So it's a general thing in any switching network, actually. If you are familiar with them, you're good. And same for GL, in any switching network. So you control the switches. If there's a closed path between the selected two nodes, the Boolean function of these two nodes becomes 1, otherwise 0. Same for the four terminal. For example, this one FL is 1, but GL is 0. There is no connected ones between left and right. Okay. Okay, again, get to the question. How can we implement a given function? So as I told you, if you have a claim that, okay, four terminal switch-based lattices can be the future, you should first prove that you can do everything, competing with these four terminal switches. To do so, you should prove that you can implement any function, Boolean function with four terminal switches. Okay, you are given this Boolean function, how to implement? Let's check. Okay, first lattice, first path,
Excuse me, sir.
X1. Yes.
Why didn't you take the approach of showing that you can implement a universal logic gate? Then your problem is solved. I don't understand why you're just showing some AND and OR gate. Why don't you implement a universal logic gate?
Good question, but the main motivation is competing with arrays. And as I explained, we know that doing something with separate gates and connecting them and spaces and everything so costly, and this cost increases terribly when you get to the 5 nanometer. So the motivation is that do it with a single network as much as you can. So if you implement AND and OR, there will be no difference, even worse than the regular computing. So here, for example, you have 16-bit adder, just single network, because fabrication is easy, spacings. There's no spacing, so no need to obey the rules, very strict rules in under 10 nanometer. It's very bad. That is the motivations. Clear?
Yes, sir. Thank you.
Okay, this is the first. Second one, X1, X4. Third one, X1, X2. Fourth one, X1, X2, X3, X4. And there are also other paths, but these are redundant. For example, this path with the dashed line is covered by the path on the second column on the right-hand side. So we don't consider these paths, especially in this slide, because they are all redundant. Okay, what is the end? What is the solution? This lattice implements a function x1, x2 or x1, x4. So not good. So this function, given function, target function is very basic. If I tell you implement this function with CMOS, two terminal switches, you can do it immediately. So you can do x1 in common in parentheses, x2, x3, or x4, and you do it immediately. But in lattices or arrays, similar problems happened in diode, in FAT and memristor-based arrays also. Not quite straightforward. And we see a problem here, challenging. Let's check the second one. X1, X4 again. Third one, fourth one. But this one is good. So even for this simple problem, it is not that straightforward. So meaning that you cannot solve this problem with a try and check type algorithm or with a algorithm that randomly generates some lattices and assigning variables. Not that easy. It's a very challenging problem. And because number of paths grows exponentially with the number of products in the function. Okay, the question is, okay, how to solve this problem? And I came up with the solution. You're given a function. Start with this function and its dual. What is dual? Dual of a function, you interchange and or operations. That's it. You get the dual. For example, dual of ft is this. So you use ors instead of ands, you use ands instead of ors, you will get the dual. Okay, so you compute the dual. Second step, assign each product of ft to a column, assign each product of ft dual to a row, meaning that you need a lattice having the same number of products as the number of columns and the number of rows as the number of products in ft dual. So as a result here, we need a 3 by 3 lattice because 3 products in ft, 3 products in ft dual. And then we assign products here, assign them. Complete an intersection set. So what is common? x1 common, x2 common. And then, for example, there is an example, x1, x4, and x2, x4, x5. What is common? What is the intersection? x4. And select a literal from an intersection set and assign to the site. So here, for the specific example, all these intersection sets have just one variable or literal, but it might be multiple. In case you have multiple literals in a set, you can select any of them. So it doesn't matter. Then I guarantee that this lattice implements your target function. So with this step-by-step algorithm or way to explain the computing, you can implement any Boolean function, which is nice. Another example, there is a given FT dual. So here, gray sides are the sides having intersection sets of multiple variables. For example, this one has a set of x2, x3, x4 now. But you can select x2, x3, or x4, it doesn't matter. So at the end, this lattice implements your target function. Okay, so, and after this, I didn't add other slides, but after this, so we developed set-based algorithms to improve our performance of this algorithm, and we got lots of publications on this. But the problem is that, as I told you at the beginning, how about the technology? So, okay, you did it, 4-terminal, nice, good scheme, good paradigm, but if there is no technology, there will be no future, right? So how about the technology? And here we show that with the current CMOS technology, you can implement switching lattices, which is really nice. So CMOS is the commercial technology, and you can implement switching lattices. Here is the implementation. These are the layout pictures. And with using pseudo NMOS dynamic or photodynamic, you can implement any functions. Here are our layout pictures, 65 nanometer CMOS. Same logic function with conventional CMOS and crossbar base 65 nanometer CMOS lattice. 2x array improvement. And these are real results from a commercial cadence tool. These are the detailed results. So indeed, in average, our array is much smaller, 2x. Delay is comparable and power is smaller. Okay, what is next? Now, we are still working on this. We have a project with University of Massachusetts. We started this fabrication because there are some structures that cannot be fabricated using commercial tools. Even you can put on the layout, you cannot test it because there's no such device in cadence, right? Because 4-terminal switch is new. And what is the solution? Okay, let's fabricate them. For example, this H type and the square type, you cannot implement using CMOS. Okay, let's fabricate them by ourselves. We started these fabrications before the pandemic and still working on this. We have some good results, bad results, but because fabrication is challenging. So in the clean room, you do everything. Now we have some good curves and we are using silicon on insulator technology. And what is the feature here? I mean, if we have good enough results to motivate us for the future, we want to go with this gate all around and vertical 3D structures using switching lattices. This is our group. That is the end, and thank you.